The universe, vast and majestic, is home to billions of galaxies and countless planets, each formed through complex and fascinating processes. Understanding how planets and galaxies are made requires delving deep into the physics of the cosmos. Galaxies are essentially massive collections of stars, gas, and dark matter bound together by gravity, and they come in various shapes and sizes, including spiral, elliptical, and irregular. The formation of a galaxy begins within vast clouds of gas and dark matter, known as halos, that permeate the early universe. These gas clouds, mainly composed of hydrogen and helium, begin to collapse under their own gravity. As the gas collapses, it heats up, forming a proto-galaxy. This early structure continues to attract more gas and dust, eventually leading to the birth of stars, which become the building blocks of galaxies. Stars, the primary components of galaxies, form within dense regions of gas known as molecular clouds. These clouds, often called stellar nurseries, provide the raw materials for star formation. When a molecular cloud experiences some external disturbance, such as a shock wave from a nearby supernova, regions of the cloud collapse, creating dense cores. As these cores collapse, they form protostars, which begin to heat up due to gravitational energy. Over time, the temperature and pressure at the core of a protostar becomes so intense that nuclear fusion ignites, transforming the protostar into a fully fledged star. This process of nuclear fusion, where hydrogen atoms fuse to form helium, releases an immense amount of energy, causing the star to shine brightly. The material surrounding a newly formed star often flattens into a rotating disk of gas and dust, known as a protoplanetary disk. This disk is where planets form. Tiny particles of dust collide and stick together, gradually growing into larger bodies called planetesimals. These planetesimals continue to collide and merge, forming protoplanets, which are the seeds of planets. The type of planets that form depends on their distance from the star. Closer to the star, where temperatures are higher, rocky planets like Earth and Mars are more likely to form. In contrast, farther from the star, where it is cooler, gas giants like Jupiter and Saturn form, composed largely of hydrogen and helium. The formation of planets is a violent and chaotic process. Collisions between planetesimals can be catastrophic, destroying early planets or throwing them out of their orbits. Over time, however, the protoplanetary disk clears, leaving behind stable planetary systems orbiting their parent stars. While individual planets form in protoplanetary disks, galaxies themselves evolve over billions of years. The Milky Way, for instance, is about 13.5 billion years old. It likely formed when smaller protogalaxies merged, attracted to each other by gravitational forces. This process of galactic mergers plays a crucial role in shaping the structure of galaxies, often creating the spiral or elliptical shapes we observe today. In addition to stars and planets, galaxies contain a mysterious form of matter known as dark matter. Dark matter does not emit light, making it invisible, but its presence is inferred from its gravitational effects on visible matter. Scientists believe dark matter makes up about 85% of the total mass of the universe and plays a critical role in galaxy formation. Galaxies also contain supermassive black holes at their centers. These black holes, millions or even billions of times the mass of the Sun, significantly influence their host galaxies. As matter falls into the black hole, it heats up and emits tremendous amounts of energy, which can affect star formation in the galaxy. Star formation in galaxies is not uniform. Some regions are more active than others, and certain galaxies, known as starburst galaxies, experience periods of intense star formation. In these galaxies, stars form at rates hundreds of times faster than in normal galaxies, consuming vast amounts of gas in the process. The interaction between galaxies can also trigger star formation. When two galaxies collide, their gas clouds are compressed, leading to the rapid formation of new stars. However, these galactic mergers can also disrupt the structure of the galaxies, sometimes creating tidal tails of stars and gas that stretch out into space. Over time, galaxies evolve. Small galaxies are absorbed by larger ones, stars burn out and die, and gas supplies dwindle. massive stars end their lives in spectacular supernova explosions, spreading heavy elements like carbon, oxygen, and iron into space. These elements are the building blocks for new stars, planets, and even life. The death of a star, especially a massive one, can lead to the formation of a black hole or a neutron star. If the remaining core is massive enough, the gravitational collapse creates a black hole, an object with gravity so strong that not even light can escape. In other cases, the core forms a neutron star, an incredibly dense object composed almost entirely of neutrons. The remnants of supernova explosions, such as the Crab Nebula, are beautiful clouds of gas and dust that expand outward from the dead star. These nebulae are often the sites of new star formation, recycling material back into the next generation of stars and planets. The universe is a dynamic place, with galaxies constantly moving, evolving, and interacting with each other. Our own galaxy, the Milky Way, is on a collision course with the Andromeda Galaxy, the closest large galaxy to us. In about 4.5 billion years, the two galaxies will collide and merge, forming a new, larger galaxy. Despite the violent nature of galactic collisions, it is unlikely that stars or planets will collide during the merger because of the vast distances between them. However, the gravitational forces involved will reshape the structure of both galaxies, potentially triggering new waves of star formation. The study of galaxy and planet formation has been revolutionized by modern technology. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope allow scientists to peer deep into space and observe galaxies and stars forming in real time. These observations provide valuable insights into the processes that shaped our universe. Recent discoveries have revealed that planets are incredibly common in the universe. The Kepler Space Telescope has discovered thousands of exoplanets, planets orbiting stars outside our solar system. Many of these exoplanets are in the habitable zone of their stars, where conditions could be right for liquid water and, potentially, life. One of the most exciting questions in science today is whether life exists elsewhere in the universe. With so many planets in our galaxy alone, the possibility of finding extraterrestrial life seems more plausible than ever. Understanding how planets form and evolve is crucial to answering this question. In conclusion, the formation of planets and galaxies is a process driven by the fundamental forces of nature, from gravity to nuclear fusion. These processes create the beautiful and diverse structures we see in the universe today, from spiral galaxies to rocky planets. As our understanding of the cosmos continues to grow, we gain a deeper appreciation for the complexity and majesty of the universe and our place within it.
The cosmic ingredients necessary for the formation of celestial bodies, from gas clouds to stellar nurseries. We'll dive into the stages of stellar evolution and the forces at play that lead to the beautiful diversity of worlds we see in the universe today. To understand the formation of celestial bodies, we must begin with the cosmic ingredients that are essential for their creation. The universe is filled with vast clouds of gas and dust, known as nebulae, which serve as the nurseries for stars and planets. These clouds are primarily composed of hydrogen and helium, the simplest and most abundant elements in the cosmos, along with traces of heavier elements like carbon, oxygen, and nitrogen. These materials are the building blocks of everything we observe in the universe, from stars to planets and even life itself. The process of celestial formation begins when a gas cloud becomes gravitationally unstable, often triggered by a shock wave from a nearby supernova or a collision with another cloud. This instability causes the cloud to collapse under its own gravity. As it collapses, the cloud fragments into smaller, denser regions, each of which can become the birthplace of a new star. These dense regions are known as molecular cloud cores, and they are where the magic of star formation begins. As a molecular cloud core collapses, it spins and flattens into a disk-like shape due to the conservation of angular momentum. At the center of this disk, the gas and dust heat up, forming a protostar. A protostar is the early stage of a star, where nuclear fusion has not yet begun. The temperature and pressure in the core of the protostar continue to rise as more material falls onto it from the surrounding disk. Once the core temperature reaches around 10 million degrees Celsius, nuclear fusion ignites, and the protostar becomes a main sequence star, marking the beginning of its life as a fully formed star. The surrounding disk of gas and dust, known as a protoplanetary disk, is the birthplace of planets. Within this disk, tiny particles of dust collide and stick together, forming larger and larger clumps. Over time, these clumps grow into planetesimals, which are the building blocks of planets. Through a process called accretion, planetesimals merge to form protoplanets, and eventually, full-fledged planets. The type of planets that form depends on their distance from the central star. In the inner regions of the disk, where temperatures are higher, rocky planets like Earth and Mars form. Farther out, where it is cooler, gas giants like Jupiter and Saturn can form, with thick atmospheres composed mostly of hydrogen and helium. The diversity of planets we observe today is a result of the different conditions that exist within each protoplanetary disk. Factors such as the amount of available material, the distance from the star, and the presence of other celestial bodies all play a role in shaping the final outcome. Some disks may form large, gas-rich planets, while others may form smaller, rocky worlds. The interplay of gravity, temperature, and material composition creates a wide variety of planetary systems, each with its own unique characteristics. In addition to planets, the process of stellar evolution also gives rise to a wide range of celestial phenomena. A star's life is determined by its mass. Small stars, like red dwarfs, can burn their fuel for trillions of years, slowly fading away as they exhaust their nuclear fuel. Larger stars, on the other hand, have much shorter lifespans. Once they exhaust their hydrogen fuel, they undergo dramatic changes, swelling into red giants before shedding their outer layers and leaving behind a dense core known as a white dwarf. In the case of the most massive stars, their fate is even more spectacular. After burning through their nuclear fuel, they undergo a catastrophic collapse, triggering a supernova explosion. This explosion is so powerful that it can outshine an entire galaxy for a brief period of time. The remnants of the explosion, rich in heavy elements like iron and gold, are ejected into space, seeding future generations of stars and planets with the elements necessary for life.
The force that governs the formation of celestial bodies is gravity. Gravity is the driving force behind the collapse of gas clouds, the formation of stars, and the orbits of planets around their stars. It is also responsible for shaping galaxies, from the grand spirals of the Milky Way to the elliptical galaxies scattered throughout the universe. In addition to gravity, other forces, such as radiation pressure, magnetic fields, and stellar winds, play a role in shaping the formation and evolution of celestial bodies. One of the key stages in the life of a star is its transition from the main sequence to later stages of stellar evolution. After a star exhausts the hydrogen in its core, nuclear fusion slows down, and the star begins to cool and expand. In this phase, stars become red giants or supergiants, depending on their mass. This swelling process can cause the star to shed its outer layers, creating a planetary nebula, which is a shell of gas surrounding the dying star. The diversity of worlds we see today, from barren rocky planets to gas giants with complex atmospheric dynamics, is product of billions of years of cosmic evolution. As stars evolve and die, they release heavy elements into space, which are incorporated into new generations of stars and planets. This process of recycling material throughout the universe is what gives rise to the rich variety of planets, moons, and other celestial bodies we observe today. Another important force at play in the formation of celestial bodies is angular momentum. As a gas cloud collapses to form a star, its rotation speeds up due to the conservation of angular momentum. This spinning motion is responsible for the flattened shape of protoplanetary disks and also influences the orbits of planets around their stars. In some cases, the transfer of angular momentum can cause planets to migrate inward or outward within their solar systems, leading to dynamic changes in their positions over time. The final stages of stellar evolution can result in some of the most extreme objects in the universe, black holes and neutron stars. When a massive star explodes as a supernova, the core that remains may collapse into a neutron star, a dense object composed almost entirely of neutrons. If the core is massive enough, it may continue to collapse into a black hole, an object with such strong gravity that not even light can escape. Black holes play a crucial role in the evolution of galaxies. Many galaxies, including our own Milky Way, have supermassive black holes at their centers. These black holes can influence the motion of stars and gas within the galaxy, and in some cases, they can even drive the formation of new stars by triggering shockwaves that compress gas clouds. In addition to stellar and planetary formation, another essential component of the universe is dark matter. Although invisible, dark matter makes up about 85% of the universe's total mass. It interacts with regular matter only through gravity, and its presence is essential for the formation of galaxies. Without dark matter, the gravitational pull of ordinary matter would not be strong enough to form galaxies or hold them together. The formation of galaxies themselves is a complex and dynamic process. Galaxies begin as small, irregular clouds of gas and dark matter, which gradually grow by accreting more material and merging with other protogalaxies. Over time, these early structures evolve into the large, organized galaxies we see today. The process of galactic mergers continues to shape the universe, with galaxies constantly interacting and combining to form even larger structures. In summary, the cosmic ingredients necessary for the formation of celestial bodies include vast clouds of gas and dust, gravity, angular momentum, and the forces of stellar evolution. These processes, driven by the fundamental laws of physics, give rise to the incredible diversity of stars, planets, and galaxies we see in the universe. From the birth of stars and molecular clouds to the recycling of material through supernova explosions, the cosmos is constantly evolving, creating new worlds and reshaping the galaxies that contain them. From this, we can truly grasp the greatness of God in the creation of planets and galaxies.